All right, welcome back to our last day of derivatives. Next week we'll start into integration, which is the opposite of what we've been doing. So we're going to be going backwards after this. So the better you understood derivatives, the easier 13 will be as we go backwards. So I thought for today I'd just choose a word of the day. We'll go with maxi-min. That's not maximum. I didn't misspell it. It's maxi-min. That's a word I made up that involves both maximum and minimum because that's the topic of today. We're going to look at how to use calculus to find maximum values and minimum values. We'll focus on some applications. The first part is the theory behind it, how we use a derivative to do it. Basically, we set the derivative equal to 0, but we'll go through all of those steps. Second part is looking at some application problems where we want to either minimize something like cost or maximize something like area that a fence encloses. So those are the types of problems we'll look at. The other thing I wanted to do is a number of you have gotten test corrections into me, and if you haven't, you could get that into me next week. You can submit them online if you'd like. I've got some forms sort of set up. It doesn't necessarily have to, it's not an official form or anything, but basically I just need to know the question number, what was the question, and then work out the problem for me to show me you understand. And the more you can kind of explain, the better. Okay, and even if you didn't understood, especially if you kind of knew what you were doing, but you just sort of chose the wrong answer for whatever reason, that's good to explain. But if you didn't even know what you were doing, but now you do, the more you explain to me, the better the more I can do. You'll get at least getting the correct answer gets you half the points back at the minimum, but then a good explanation can push up those points. The other thing is on the test, and actually everybody but one student took the test, which was really good. I contacted that one student. I haven't heard back. So if you are that one student, please contact me, and so we can see if we're going to continue or not. But other than that, everyone's taken at least once. A few people have wanted to take another version of it, and I can understand that. But what I'm asking is for test corrections first. So give me the test corrections. We'll process that. That shows some understanding, and then we can do an alternate test later, probably next week. This weekend I will make up the test for 11 and 12, which is derivative stuff. So next week, or over the weekend, you'll probably see that test come up. You'll see a practice test come up. You'll be ready for that one. And I will also update all the test corrections I've got in there, so kind of give you a feel for about where you're at. And again, with the extra credit, most of you are doing very, very well. I wanted to take a look at the syllabus. Well, actually, I already have, but I want to look at it with you guys. So the first thing, let's go back up here. Again, it has been a while since I've taught it. I took this over. I wasn't planning to teach summer school at all, but then my teacher who assigned this had some other things come up, and I tried to give it away to somebody. Nobody else wanted it, so I said, well, I'll stick around and teach it.
Thank you.
Well, thank you. It's actually been kind of fun. I like doing this again. So what I did is I found out here, looking at the competencies, that's kind of, this tells me what I'm supposed to teach you guys, or what we're supposed to do. And finding derivatives and functions using both definition and theorems. We've done that. That was pretty much mostly chapter 10. So that took care of that first competency, check. Use derivatives to solve and analyze application problems related to business, life, and social sciences. We're covering most of those tonight. So the second part of 12 does with application problems. There was some application problems in 11, weren't there? Do you remember? I think there was a few cost and revenue type profits. So that's a business application. So after tonight especially, we could check that one off. So we did that. Use technology to model solve. So we've been using graphing calculators, haven't we? That's technology as a tool to do all of this stuff. The ones we haven't done, find the integral functions using theorem. So that's going to be chapter 13, which is 3 sections. Use the integral to solve and analyze application problems related to business, life, and social sciences. By the way, economics is a social science. Economics is also business. So if we cover economic applications, we've pretty much covered all of those. So as I looked over the sections we have left to do, I guess I should take off these. I am thinking, if it's okay with you, so notice we've got the indefinite integral, the integral, integral, integral. So these are all kind of the theory of integration. We have these economic applications, which covers all the applications parts. These are two additional techniques, or kind of special techniques for doing integration. The competencies don't say we technically have to do those, but I think they're good things to have. I was thinking I would just take the points and just make them extra credit. So I would leave them in there if you wanted to do it, but not necessarily. I wouldn't do any class on it because they're not going to be required. Does that sound reasonable? But for those who might find a need, and just to tell you, probably if you're going to be a math major, those would be helpful. But for business or social sciences, it's probably not a technique that's going to be of any great value, because all of those things can be done with numerical integration. So you plug it in a computer, you get your answer, you've got what you need. Okay, but they do have the techniques of learning how to do it mathematically would help you if that's what your major was. So I'll leave them in there, but the points will be in the grade book as extra credit. So you'll see that above on the grade, it'll say they're worth 0 points. But if you do them all, you could earn up to 20 extra credit points. Does that sound good? So then what we can do is we can move this economics applications day a day earlier. I could talk about it. We could go over, that gives us one section. I could review, it gives me a little bit more time to review. And then that gives us this last day here, because remember, I'm sort of leaving, at least physically. My heart will still be here with you, but I'll be leaving, and I'm going to do some online stuff so that you could, because this is a hybrid. We actually have, the way we scheduled this, we have more hours than we need to qualify as a hybrid class. So I said, well, let's do the rest of the class as the online portion. So what I would do is I would do online reviews for that last test, and a lot of you'll be in the position, because it's really just going to be a test on chapter 13 with maybe a few economic applications in there, nothing too major though. So it's primarily going to be over those 3 sections in 13. And if you've done well on this first one, you'll probably do well on the next one, because I think you'll find the next test will be a little bit easier. And then, which means you will probably also do better on that one, and so you don't need to take the final. For those who maybe need to take that final, I'll have something for them. I'm hoping though that between test corrections and maybe retaking the tests, everyone will do well enough that they would be satisfied with their grade and not need to take the final. But because that's what I always like to do. But if we need a final, I'll have it there. But again, my goal is for most of you not to have to even worry about the final. You've taken tests on each of the sections. You've proved your value, your ability to do them. I think that's plenty fine. Of course, if you still want to take the final, I won't turn anyone down, but you wouldn't have to. Yes?
So does that mean there's a total of 3 exams instead of 4? Was there originally 4?
Well, I think there was originally 3 with a final exam.
Got it.
But what I've done, at least I think, I sometimes don't read what I wrote, so I might be wrong. That was my intention, 3 exams and a final. And then what I'm doing now is if you get well enough scored, and if you're up in the higher 80s to 90s by the time you've done test corrections on the 3 tests as an average, then you won't need to take the final exam. And then again, with these extra credits in there, basically, well, I'm going to have to do some adjusting in the total score, but if you've got 90% in the class, and there's been enough extra credit, so even if your test scores aren't up there, if you do the extra credit, you could push yourself where you wouldn't need to do the final exam. Okay. But I think so far from what I'm saying, it's pretty good results on the I'm very pleased with the results on the exam. Let me put it that way. So you all doing well, especially with the corrections. Yes.
So what day would the class technically be over then?
It's still technically over on July 19th, as everything's supposed to be done, but you could be done sooner than that. So if you finish up everything, yeah, you could be done a couple, 2 weeks ahead, certainly.
Okay.
And maybe if I get my act together and get the test posted, and that's what I would plan, is maybe by July 3rd, I'd even have that third test, so you could maybe take that and almost, you could be done 3 weeks early. Pretty close to it, if you want. Or you could just, take the time. There'll be videos to go through, and so there'll still be instruction available so you understand. So I don't want to push anyone to rush through anything, but yeah, the possibility of getting done certainly 2 weeks, maybe 3 weeks early, or take the time you need, and again, then you're doing mostly online. I will still, because I do have a substitute who said she would take the week of July 17 for me, so there'll be a person here for anyone who might need some additional one-on-one instruction on anything. Okay, but again, it'd be nice for me, nice for you if you're already done and you got your A, and if you don't need it. But if you do, we'll have support.
Shucks, if we must.
Yeah. Yes. Okay. So thank you for your input. It helps, because I was just sort of thinking it through as I was talking with you, and nobody objected, so I guess it was good thoughts, huh? Okay. That's usually what I feel. Good energy. Keep going. Okay. So when we're going to look at maximum minimums, I'm going to pull up the textbook, and we're just going to look at the textbook's actual definition. And we'll look at a few of the graphs that they've got for the understanding, and then we will work some problems and just look at the technique. So this should go actually fairly good, because the technique involves pretty much plugging numbers into a function, which we've done that's algebra, and taking a derivative and finding where it's equal to 0. And if you can do that, you can find a maximum and a minimum with a few of the rules that the book brings out. Okay, what do I want to do here? So we're going to go into 12.1, and there's actually only 5 homework problems for 12.1. There's some that, there's a couple multiple parts to them, 3 and 4 parts to them. But I'm just going to go with this first one. Let's just get to the textbook, and I'll explain basically what we're doing and why we're doing, and sort of why it works. Let's see. Let's get this out of the way. Spread that open, and this page. So here's the definition for what we're going to refer to as relative extrema. Extrema just means extremes, the highest and the lowest. And relative just means that it doesn't mean it's the highest high or the lowest low, but relative to the stuff around it, it's a high point. Okay, so I came from Oregon, and I was in the Willamette Valley, so we had mountains on both sides, and up to the mountains there were hills. The hills were sort of maximums locally, but there were mountains that were taller if we drove a little bit further. So that's the idea of a relative extrema. For the area, it's the highest point or the lowest point. And so we'll just walk through this definition. And again, this is mostly for mathematics people, majors, but just to understand it, it's just saying that if we have a place, some x value, they'll call it r, so some place where this exists, and if you look, basically this interval, if you look to the left and you look to the right, you subtract a little, you subtract h and you add h. So you go a little bit to the left, a little bit to the right. What ends up happening is that the function value, the y value at that r, is bigger than or equal to all of the other y values for all the x's around it. So it just says it's the top of the hill. The key part here, though, is a constant works that way because it could be equal to as long as it's the tallest or equal to all of them. So you could have a flat, like a mesa, could also be defined as a relative maximum. And the definition for a relative minimum is all the same stuff, except they change the direction, say that the function value is smaller than everything else around it. Kind of makes sense? You're either higher than everything else or you're lower than everything else, at least around you, and that's what makes that point a relative minimum or a relative maximum. Okay, so we've got some examples up here, and so you can kind of see this, if you just think of mountains or hills, it's the top of the hill, or this little point here, this spot here could also be a relative minimum because it's lower than the rest. The other thing that can happen is if you get to the endpoints, those could also be places where you have a relative maximum or relative minimum. Again, as long as it's bigger or smaller than all the others. So basically what we came up with is there's a couple possibilities. The endpoints could be your minimums or maximums. In the middle of it, in the function, you could have minimums and maximums and relative ones, and you could have multiple ones. Like I would say about here is a relative minimum, up here is a relative maximum, there's a relative maximum, there's a relative minimum at this point. Is this, let me ask you from our experience before, is this point here differentiable? Because it comes to a sharp point. It's not, because it's just, well, it's not. We don't need to explain it. But sharp points we talked about because you could draw multiple tangents through it, so it's not technically not derivatable. You can't take its derivative. So they got an example in there that could happen. What you're going to see is a lot of this, you can tell minimums and maximums. One of the easiest ways to do it is to graph it on your graphing calculator. And when I was taking calculus, we didn't have graphing calculators, so we had to do this all blind. So you learn a first derivative test, a second derivative test. You had to do this like with a blindfold on because you never saw the graph. Now that we can graph it, that's usually the easiest way to do it. Just graph it, and you'll see where they're at, and then you can use some calculus to find it as well. Okay, so those are the places we're going to get relative extrema. Okay, so and if we're defining something especially as a relative extrema, what would be the opposite of something that was a relative extrema?
Absolute.
Good, you got the words even. So there's also absolute extremes, which means the maximum and the minimum. Okay, and so we might see here, this point here is not just a relative extreme, it's also an absolute extreme. And I guess we would just classify it more as an absolute, because it is the tallest of the tall. Absolute. And this one here looks like it's probably the absolute minimum. So that's another thing is there can be absolute minimums and absolute maximums. So this was an absolute max, and this one looks pretty close to being an absolute minimum. Okay, so and that's pretty much what the questions are going to ask you. Is we're going to be given a function, and we're going to be asked to find the places where we get either a relative maximum or minimum, and then to identify it as whether it's a relative maximum or min, or whether it's an absolute max or min, or whether it's nothing. Because it could actually, there's one little case where sort of this all seems to happen, but this part or this part doesn't work. Okay, so there are some places, well, we'll just move forward on this. There's some places where this doesn't work. And I'll show you what that looks like in a graph here if I can see if I can. And then just kind of, they talk about things that maybe if it's not on a closed interval, we're not given an interval, we're looking from negative infinity to positive infinity. It's also possible that we never have an absolute maximum because the function shoots off to infinity. So it's possible that absolute extrema don't exist. Okay. Now in this particular quadratic, there is an absolute minimum, but there is no absolute maximum because it goes off to infinity. Okay, so that's something that could happen. And the nice thing about most of these homework problems is they've got, at least you find the places where these maximum and minimums occur, but then you identify them as either relative or absolute. You'll see those. And again, remember you get 3 tries, so if you've got them wrong, you can play with it a little bit to try to see how it works. Yes?
For maximum, can we ever get infinity?
If you get infinity, then I think they call that as a D and E, that there is no absolute maximum, because the idea of infinity itself is it's really not a maximum. It's a place you're always trying to get to, but you never really get there. So they kind of stick to that mathematically. There's a whole other mathematics where you would say, yeah, infinity is a place or it is a number, and you can sort of conceptually get there, and then you could call that the maximum. But I think in here we'll go through the homework problems on the drop downs. I think it says there isn't one, but I didn't look real closely myself. So, and then there's one other thing. So notice here, what kind of a tangent line would go through this minimum? What kind of tangent line would go through here? Through this point.
Just a straight
Horizontal line. What kind of a slope does a horizontal line have? A slope of 0, right? So, and that tangent line comes from what? How do we get the tangent line or the slope of the tangent line?
derivative.
We take the derivative, we find where it's equal to 0, that gives us the x value. So yeah, so basically to find maximum and minimums, we take the derivative of the function, find where it's 0, because that's what we're looking for. Where's the slope of the tangent line equal to 0? So those are our first candidates for maximums or minimums. Again, if we're given a boundary line, so an interval, we check the left and right interval, the boundaries as well, because those might be maximums or minimums. But other than that, we take the derivative, set it equal to 0, find all the places that happens. And again, if it's quadratic, it could happen in 2 places, right? If the derivative is cubic, it could happen in 3 places. But we don't get too bad of derivatives here. So we find those places where it could possibly happen, and we check out whether they're a derivative, or if they're a minimum or maximum. And again, one of the best ways to do it is to go ahead and just graph the original function too, because you'll see whether it's a minimum or maximum from the graph. And I think this next page will take us, oops. To show you so those are okay, those are okay. So again, this is just showing you your book. Go ahead and review it. You could have absolute and relative minimums and max at the endpoints, at what they're calling stationary mins and max, and then they've got one they call singular, but that's when it comes to a point. And really the only function we have that can do that would be the absolute value function. So if you see one with an absolute value, you could potentially get a singular min or max. Otherwise, everything else is really going to be what they call stationary. And I'm not going to put that kind of stuff on the test, so I'm not going to test is it stationary or is it singular or is it, so we'll stick with that. But there's one more thing, and I know it's here. It's possible that we take the derivative, set it equal to 0, we get a place, but it's actually not a minimum or a maximum. And again, the best way to do is to take a look at the graph, and let's see if they show one of those. I think it was here. Nope, it's not that one. Just kind of take you through the textbook. Okay, so it's like right here. There's places where when you take it, it's the derivative's actually 0, but what it is it's you'd find out later. It's more of an inflection point. So it's not that it's a minimum or a maximum, but it becomes an inflection point. And basically it's a place where it flattens off. So again, take a look at the graphs, and if you find a place where there's the first derivative is 0, check it out. And so what they do is they tell you, if you look to the left, to have a minimum or maximum, so let's see, to have a maximum, you have to be increasing on the left and then decreasing on the right, right? Because you came up the hill, see, left, came up the hill, and then you went down it. That's a maximum. If you went down and then up, that's got to be a minimum. So it just, you kind of look at where your critical point is, where the graph, where the derivative is equal to 0. You look a little bit to the left, a little bit to the right, and see what's happening. Now, if you don't get that happening, if they're both going down or both going up, that's not a minimum or a maximum. It's what's called an inflection point. Okay, so there might be one or two of those. Okay, so they throw those in there, a little tricky. But again, if you look at the graph, you'll see those places because what they look like is they look like a place that's sort of flattened out for a little bit. But they don't have the characteristic of a bump, either down or bump up. Okay. How are we doing so far? Is any of this making sense? Okay. It's just like, this is a great one. Just it's like being on how many of you like roller coasters? I used to when I was younger, but I get sick on them now. But yeah, I used to just love the big ones. I lived in Oregon. They had this one, Oaks Park. It had one of the historic wooden ones, one of those huge wooden ones, and I think it was like one of the last ones left. And by the time I was old enough to go on it, they wouldn't let you go on it because the wood was so old. They were afraid someone's going to die, and probably would have. But I just always went by that and said, I want to go on that roller coaster. But that going down and up, you got minimums and maximums all the way along there. And if you think about going on it, that speed you get going down, that's the rate of change. That's your derivative is speeding up, and then you hit a point and it slows you down, right? And then sometimes at the top you almost feel weightless, and then you start going back down. You're actually feeling a derivative when you ride a roller coaster. So that's your homework assignment. Sometime this summer, if you can, go ride a roller coaster and think about calculus. And think, oh, here's the derivatives going down and up. That's the best way to understand calculus, is to experience it. Okay, so I think this is pretty much it with the techniques. So let's just kind of take a look at what we would do. I'm just going to minimize that for now. I've got a couple examples that we'll just go ahead and start with, and we'll analyze it in a couple ways. I'll even use the calculator. And so here's one of the questions. We're given a, let's see, where is, we're given a function, f of x, equals 3x squared minus 12x plus 3. And they give us a domain for this function going from 0 to 3. Okay. And the question asks to find the exact location of all the relative and absolute extrema in the function. So find where there's maximums and minimums and so forth. So first of all, just, yes?
If you're given a domain, isn't that automatically a relative?
What do you mean, what's relative?
The maximum and minimum of the domain, within the domain?
You mean the endpoints of the domain, maybe? Or just...
Well, anything in that range from 0 to 3 would be relative as the graph continues on.
Right, but as far as we're concerned, there is nothing else that exists. So it's possible that whatever part of this parabola we have, it could, the relative minimum could also be an absolute minimum or maximum. So they could be there could be some absolutes in here. It just depends on what part they give us. And they could occur at the endpoints, depending upon which part which part they're giving us. And that's why it's going to be best to take a look at this and then think of it. And I'm going to show you the way I analyze this. I'm going to change my window. My x minimum is going to be 0. My x maximum is going to be 3. Because I don't want the rest of the graph to even mess with me. Because in this world, the rest of the graph does not exist. Only from 0 to 3. That's the whole universe for this one. Okay, so that's what we're going to do is before we start to try to analyze this in any way, let's just see what it looks like. Then what we'll do is we'll come back, we'll plug in the endpoints 0 and 3 to see what kind of y values we get. And then we'll also look in the middle points. We'll probably take the derivative, set it equal to 0, and see if there's a minimum or maximum in there. But sort of the first step on these, if you'll just graph it first, then I think you'll find you'll be in best shape. So I'm going to come over, let's see, how do I do this? I come over here to my camera where we've got our graphing calculator ready, and that's where we're going to put this problem in here. I'll take this one out, and I'm going to go 3x squared, arrow over, and then minus 12x and plus 3. So that's a quadratic. Before I go to graph it, I'm going to go to my window, and I'm going to make my x minimum the left side of the domain, which is 0, and I'll make my x maximum the right side of the domain that they give me. And if they don't give it to me, maybe just make it 10 or something, but I'm going to restrict my domain. Now I'm not sure if... What's that? Then go to window. Yeah. And then make x minimum 0 and x maximum 3. And what that's going to do is make your window come in and just focus on the domain. Now I don't know as far as y minimum, y max, so I'm just going to leave it at 10. I'm going to hit the graph button and see if it's good enough. Yeah, it pretty much fit it. So now we see this. See, I don't think I can draw on that. Or can I? Let's see. Maybe I can draw that. Let's see. Although, let's see. People watching the video will have to tell me whether or not this is coming through. I'm not sure. It looks pretty good for us, right? So what do you see here? Here's one of the boundary points. What's this going to be? 3, and it's going to be what kind of a maximum? Will it be a relative or an absolute? Absolute, because there's nothing else taught. You could just kind of visually see this, okay? We'll look up on the table to get the exact value, but yeah, it looks like maybe it's 3. but this is definitely going to be an absolute max, nothing higher. What's going to be this? It's an absolute minimum. It's also sort of a relative minimum. We would typically think of it, but there's nothing else smaller than that. So exactly, this is going to get called an absolute minimum. And since it's in between, the way we find it is we're going to have to take the derivative, set it equal to 0, and it will tell us this x value. Now looking at this graph, it looks like it's probably 2, and it probably is. But we'll also take the derivative, set it equal to 0, and that should give it to us. So we're kind of verifying things visually, and then we go do the math and come back. And then what about this guy or girl? I don't know, is it a guy or girl? Person, this point, this thing over here. What would that be? Nothing? Something? Right. So infinity, you're thinking, again, that's why I wanted to restrict this domain. There's nothing past 3. So you're right. The graph itself would keep going off to infinity. But because we stop at 3, it is actually also a relative maximum, because it is a maximum for its area, for its neighborhood. It's the big guy. So you know, if you're a bird, that's where you would go fly to that place, because birds always like to go to the tallest place, right? So that's going to be a relative maximum, though. So it's a maximum, but it's relative. It's not the tallest. So over here, we're going to get a relative max. So notice the endpoints give us our maxes. One's an absolute max, the other's a relative max, and then in between, because it's going downwards like that, we actually get an absolute minimum as well. So the nice thing is if it's on the endpoints, here's the easy way to find it. We're going to go to our table. Actually, let me do this. Let me take this off or record it. Let's see. I'm going to hit our table, and table is a shift graph, so second graph. Now, if you notice, I still have mine on ask. So for this stuff, it's maybe better to go to table set, change it to auto, and I'm going to have the table start at 0 because that's what the end of and go up by 1s. Okay, so I now got 0, 1, 2, 3. So you can see on here at 0, I can, my endpoints. Here's an endpoint. Here's the other endpoint. So we've already labeled these as being an absolute maximum, so a y value of 3, and a y value of -6 as being a relative maximum. And then we look at 2 as being -9, and I'll bet you that's what we're going to come up with as far as our relative minimum, but we're going to do the calculus to make sure to check it. Okay, so this is kind of, from the graph, it looks like 2 is probably the relative minimum. Okay, and you could even use your calculator at this point. So you could do all this stuff with a calculator. You could find, you could use, there's a tool to find a minimum. You could find it, and that would give you your point too. Okay, but we're just going to use the calculus because part of math is we still teach you stuff from 500 years ago. So why not teach you stuff that needed to be done 20 years ago, even though now we've got technology that does it better. Okay, so we're going to verify that with the derivative. Okay, so let's see. I'm going to pull this back over here to my side, and I'm going to switch. Go there, and then I'm going to take our recording. I have a feeling the recording isn't, so if you watch this recording, you probably don't see anything that I'm doing on the calculator, but So you guys get a better show than probably everyone else, but we'll see. Okay. Oops. We got to go back, right? There we go. So this is what we want to work with. Did anyone write it down what we had at the endpoints? We had a point, well, I think it was what, 0, 6, or 3? Okay, so we looked that up from the tape. And then 3, -6. And from the graph itself, we could just label that this was an absolute max and that this one was a relative max. Okay. And then to find the one in the middle, what we're going to do is we're going to take the derivative of the function. And this is what we've been doing. So the derivative of this, the 2 comes down. 2 times 3 is 6x. 2 minus 1 is just the 1. And then this, to take this derivative, 1 times -12 is -12. 1 minus 1 is 0, so that becomes x to the 0, which is just 1. Derivative of a constant is 0, so we're done. So there's our derivative. To find where a minimum or maximum is using the derivative, we just set it equal to 0 and solve. So we take our derivative, 6x minus 12, set it equal to 0. So we're going to add 12 to both sides, solving for x. That's 0, so we get 6x equals 12. And are you surprised? Divide both sides by 6, we end up with x equals 2, which that certainly looked like the place on the graph, didn't it? We were right. And so what we would do now is plug the 2 back into the original function, which we've actually already done with our table. That's why I was looking at it. So I'm going to just kind of, I don't have to squeeze it in here, but let's just write it. It was 2, I think it was -9 from the table. If you're not sure, go look back at your calculator. And that we identified as an absolute minimum. Okay, so we used sort of calculus to verify that it was. So notice really, technically, as far as calculus is concerned, nothing really new. We're just taking a derivative, setting it equal to 0, which we've actually had you do before. We just didn't tell you that you were finding a minimum or a maximum. Okay, so that's really this whole section. You're just going to analyze graphs. So you're given things, you're given a function, take a look at it, graph it, physically look at it, try to figure out where the mins and max are just from looking at the graph itself, and then use the table to get the endpoint values and see if those are what they're supposed to be. And then for the middle ones, where there's relatives, mins, and maxes, take the derivative, the first derivative, set it equal to 0, solve for the points, and you'll get x values, plug them back in, and you'll get your points of consideration, label them what they are, and there's, again, you'll do this 5 different times, but each of the questions has multiple subpoints. Yes?
Why did we set it to 0 again?
When we set it, the derivative, when we set the derivative equal to 0, what are we looking for?
Oh, the flat.
A horizontal tangent line.
Yeah.
So any place that a derivative would be equal to 0 is saying to us, hey, this is me. I'm a max or I'm a min. And then we have to examine around it to see which one it is, because max and mins both have a derivative of 0. And then the ancients had different techniques, because they instead of drawing whole graphs, they would look at graphs this way and analyze. So far, so good. Okay, that's pretty much everything you're going to have to do in 12. Let me do a couple different examples. And I just printed up, yeah, most of the examples are just pretty straightforward like that. The only other one is, let's see what happens when we have a domain that doesn't have a boundary, so it goes off to infinity. Okay, so let me go back and save this one. And then let's take a look now at this function. H of t equals t to the third minus 3t squared, and they're going to give us a domain of -1 with a bracket, so it's included, all the way to plus infinity. Okay. So for this one, we have to go out a little bit to see what's happening. And again, if it shoots off to either positive infinity or negative infinity, then we'll actually go in and maybe do this one and let it tell us what it is. Okay. So again, to start everything, what we want to do is first, let's just graph it. Back over to our camera. We'll put the new function in, and again we'll put in x raised to the third minus 3x raised to the second. And when I go to my window now, my x minimum, since -1 is the left-hand boundary, I'm going to start it at -1, but since I go to infinity, you don't put infinity in here, that's too far. I don't know, maybe 20. You could do 10. This is kind of a do what you like, but we just want to see what happens when we go out further. Okay, so I'm going to graph it. Well, we actually didn't have to go out that far. Looks like we've got a maximum, a relative maximum, a relative minimum, and then it looks like it shoots off to infinity. And now this time the right-hand side is open, so when it shoots off to infinity, we have to kind of figure out what do they really mean. That's not really a maximum, it's just infinity. So we'll do this again. Over here. And it's our graph. Yeah, we'll leave that up there. I think that's okay. So as we come here, remember this is one boundary point. What's this going to be? It could be. Now the thing is that we're gonna have to compare. It might be smaller than this, or it might be about equal. So it's, what do we do when we have two minimums that are the same? Then I guess they're most relatives, but it's either absolute minimum or maybe a relative minimum. We'll see, but definitely a minimum. And once we get the values, we'll analyze it. Then this comes up. It looks like what's happening here. A relative maximum. Okay, definitely. And we could see there's points that go above it, so it's definitely not an absolute, but so we'll call it a relative max. And then this one, again, it's kind of, they look like they might be equal, and it could be. So we'll look what they are, but definitely it's a minimum, and it could be either an absolute minimum or a relative minimum. We just have to see what those values are from the table. And again, looking at this, it looks like possibly this relative max is occurring at x equals 0. And it looks to me, probably about x equals 2, we get a relative minimum. And we'll see, because we're going to take the derivative, but those are probably where we're going to find it. Okay. As we go off this way, is there anything we need to worry about? No, it's going to shoot off to infinity. So it's going to keep getting bigger and bigger and bigger. It doesn't stop.
If the two minimum points are the same, are they both just relative?
I'll be honest, I'm not sure. So what we're going to do is this. I took this out of the homework, so we're going to do the homework problem, and we're going to put it in, and we're going to let it tell us whether we're right or wrong. Technically, I guess they would both be absolute minimums, or max, yeah, absolute minimums, because they're equal to each other. Okay, that's my story I'm going to make for right now, but I might not stick to it if they say I'm wrong. But I would say they're both absolute minimums if they're both the same. They are? Okay. So that's what I'm going to stick with. So let's, what do we do now? Okay, so next thing to do is to go ahead and take a look at this table. So I'm going to actually, while we're here, and we need to go to -1 is -4. So actually it's probably pretty good. I got this here. So we've got a point -1, -4, which we know is either an absolute or relative minimum. And then what was the other ones? We thought at 0, 0, 0, that looks like it, and then maybe 2, negative, yeah, 2's at -4, I'll bet you. But we're going to use the calculus to verify those. But the endpoints, we just use algebra. We plug it in. Okay? So what we're going to do now, I'm going to bring the everything back over here. And then we're going to switch back to here. Okay, so we've got a few things here. So we've got a minimum here. Let's go ahead and take the derivative to find those relatives. So the relative mins and maxes. So the derivative h of t is what? 3t squared minus 6t. Okay, so we're going to set this equal to 0. You could solve it with the quadratic formula if you wanted. You could graph it, find where it crosses the x-axis, or you could factor. So each one has a t. There's a 3. We could factor out a 3t, and then there would be left a t minus 2 equals 0. So that gives us two places, either 3t equals 0 or t minus 2 equals 0. So this, divide both sides by 3, you get t equals 0, which is, again, it confirms what we saw with the graph. That's why you want to look at the graph first. It'll usually, you kind of know what you know. Okay, trust your gut feelings. Add 2 to both sides, and again, we saw this, t equals 2. And so hopefully we remembered that when, from the table, when x was 0, y was also 0. When x was 2, y was -4. And if you don't, look back on your calculator. And then again, we had that other one. I'll bring it over just so it's part of the group over here. We had at -1, which was a boundary point, -4. So I'm going to say that these two are absolute minimums, right? Because we saw that from the graph itself. They were both minimums. And they're both equal to each other, but they're both the lowest there of the low. So I'm going to call them both absolute minimums. 0, 0, what we'll call that is a relative maximum. And again, from looking at the graph, we could tell that because the graph shoots off to infinity, there's not going to be an absolute maximum. So those are the three values we've got. Let's take a picture of that, and let's see. This is the only thing I'm not really 100% sure of. And this is sort of a technique I got from my teacher who taught me calculus the second time I took it and actually understood it. He would come to class not overly prepared because he wanted to show us what it's like to do when you're not absolutely certain. And I ran into this. I said I could research it and figure out what it really is, but this is what I think it is. Let's just see if it works. Okay, so now get a clear screen. I think I've got WebAssign still open. Let's see. Let's go here. And you'll see, I printed these out earlier, so it's still giving me the same problems. This one we just did is this one right here. Now you're likely to get slightly different problems, and again, your problem that will be different is that the 3 won't be a 3, it'll probably be something else, so it'll be a little different. Find the exact location of all the relative and absolute extrema in this function. Your answer is from smallest to largest t. So that's the other things, you got to put these in a particular order. So we had, what was it? We started with -1, and it was -4. And we called that an absolute minimum. At least I did. Anyone else want to call it something different? No. Okay, so we'll see. And then we had a 0, 0, and what did we call that one? A relative maximum. And then we had a 2, -4, and Little Crow said that that's probably an absolute minimum as well, because you could have, because they're both. And I'll tell you what, they're either both absolute minimums or they'll be both relative minimums. We'll let the judge here tell us. But I think this is what I would vote for. And see, no, there's nothing else to put here. Submit the answer. Oh, probably logged me out. We may never know the answer to this question. No, you'll know the answer because you'll do the homework. Let's see. Do this. If I go back into WebAssign, there we go. But now I got to enter it. Still got the same problem. Yes, sir.
So anytime you can factor out, usually it's because you have 2 minimums or maximums.
Right. Yeah, you're going to have a quadratic. If you have a linear, so if you got a quadratic and you take its derivative, you have linear and you have no problems. But if you got a cubic, when you take its derivative, you're going to have a quadratic, and that's pretty much, you're going to get 2 possibilities. If you've got a 4th power, when you take its derivative, it's going to be a cubic, and so there's going to be 3 possible places for minimums and maximums. You got it. Yes. And if you have a 5th power, no, we're not going to. 5th power, you take derivative of the 4th power, there's possibility of having 4 max or mins. And it's just how the polynomials work.
It just meant how many times you could factor something out would be equivalent of that's how many.
Right, because however many factors you get, each of those could cause a different 0. Each of them could be a different min or max. Yes, exactly. Well, we had -4 here. We had 0, 0, and I think that was a relative max. And this one was 2, -4, and that we said was a absolute minimum. Did I get it all right? I think. Let's see. So now let's see if it'll take the answer. Hey, it did. So we answered our question. It's a relative minimum. So that's why I like this, is because don't worry about it. Don't stop. I don't want to submit. Submit. You got 3 chances, and this will kind of help you through it. It'll explore. And if you get it wrong, well, okay. I figure they probably programmed this. They must have had some experts in the room, and so they'll get all the technical stuff. But yeah, that sounds reasonable to me, right? Doesn't it? That if they're both the same, that they would both be absolutes, because there's nothing smaller. Okay? How's that? Okay. So you ready to go home? Oh, we got one more section. Okay. So now we need to look at some application problems. Okay. So this is just the same concept. What I'm going to focus on with the application problems is they're actually nothing much more than quadratics when we get to the application problems, because they're finding areas of maximizing area for building a fence or minimizing the cost of building a fence. or finding average cost and such. But I want to help you, I want to kind of talk you through a few of them so that you know sort of how to get the formula set up. Because sometimes they give you the formulas and that you work with what they gave you, but sometimes they give you a relationship, so you need to think through it, and you'll see you'll be actually working with something a little different. If that makes any sense. It will once we get there, but it's let's see, where are we? So for this one, I think, and this one has a lot more problems for us to work through, which, you know, that's fulfilling the application. So homework apps for maximum and minimum. Okay. So we're going to use these same techniques, but what we're going to need to do first is, and I've already got one right, so I practice just to make sure it all works. But let me just kind of walk you through how I did this. So one of them, one of the types of problems is called an optimization problem. So you want to either maximize or minimize some function with some kind of constraint. Okay. So in this one, the way I went about this is what we want to maximize. Blue. This is the function we want to maximize. We're given this as a constraint. Now, what are we going to do? There's 3 variables over here. Anyone have any suggestion? I mean, I think that's going to be hard to do. I guess we could use implicit differentiation, but they don't tell us anything about the rates of change, so that, you know, we get stuff that's not really there. But how can we use that constraint, the with x plus y equals 18? With the goal of trying to get rid of some of the variables. Well, 9 plus 9 is 18, and you can kind of see that that ends up being the answer too. But so we could guess and check, but say we didn't have any clue at the beginning. What can we do with that x plus y equals 18 so that we can turn our function that we want to maximize into a function with only one variable? This is the main concept, because we're going to use this a few times. Any ideas? Well, what if we took x plus y equals 18 and we solved it for either x or y? Which one would you like to solve it for?
Y.
Solve it for y? Good, that's what I did too. So we'll subtract x from both sides. And we now get this function that y is equal to 18 minus x. So if y is equal to this, what can we do with this y over here in the function? Substitution. So this is the key step that you're going to need to do on several of these types of problems. They'll give you this with another function. You have to solve it for one variable and substitute it over there. So then what we do is we take this function and we rewrite it as p equals x. Instead of times y, we want to 18 minus x. Okay. And then we want to take the derivative. Now, could we take the derivative of this with the product rule? Yes, we could, but who wants to do that, right? There's an easier way. We could multiply it out and then we don't have to use the product rule. So I would do is I would take p equals, distribute through, you get 18x minus x squared. And since we want to maximize, we're looking for a place where we get either a maximum or a minimum. And hopefully you're looking at this as a quadratic with a negative in front of it. So it's going to open downwards. It'll have a maximum. And how do we find the maximum? What's that? Solve for 0. So set it equal to 0 and solve it. So I'm going to go back up here. So we're going to say 18x minus x squared equals 0. Yes, sir.
Don't we have to set the not the derivative. Yeah. Don't we have to do the derivative with it?
You're right. Yeah. I forgot to do that. So yes, take the derivative, set the derivative equal to 0. Thank you. You saved me some embarrassment. I was going, yeah, okay. Yes, that's because we're going to get 2 answers this way, but there's only 1 answer, right? So that's what the eraser's for.
So after you distribute the x,
yes,
the 18x, then you do the derivative.
Yeah, and the distributing made it easier to take that derivative.
Right.
So now, yes, let's take that derivative. We want the derivative of the function, which is going to be much easier to solve for 0, right? This is 18 minus 2x. Thank you. So then we set the derivative equal to 0. That's good. This is what I like. Collaborative, cooperative learning. Because you're all smarter than I am, right? Okay, so then we take the derivative, 18 minus 2x. We set that equal to 0. Solve for x. So subtract the 18 from both sides. Minus 2x equals negative 18. Divide by negative 2. So we get that x equals positive 9. Then we need to take that positive 9 and we put it back into this function, and we're going to find y. Right? So we get 9 plus y equals 18, and you might already see, well, y has to be 9 as well, right? Subtract 9 from both sides, and you get that y equals 9. So x equals 9, y equals 9, but that's not what the answer wants. It just wants to know what p is. So that says when x and y, when x is 9 and y is 9, that's when we get a maximum. Okay, that's what, and we didn't look at it. I guess you could have graphed it if you wanted to, but by setting it equal to 0, this is telling us we got a minimum or maximum. So then the last step is to say, well, p is going to be equal to x is 9, y is 9. 9 times 9 is 81. Okay? So there's going to be a number of questions that you're going to be doing this. And the solving is going to be a little different, like on question 2, you've got x times y equals 10, so you'll divide both sides by either x or y, but you'll have something to plug back into the original function that you're maximizing. So then you've got one variable. That's only, I don't remember when I realized this, but I used to think mathematicians were so incredibly intelligent. They were so smart. That's why I wanted to be one. And then I learned, as I did it, that all a mathematician can do is solve equations with one variable. Now, some of them can do multivariable stuff, but I never could. So then it doesn't look like it. So everything we do is basically getting it down to one variable. So we use that constraint, get it either equal to x or y, and substitute back in. Okay. Take the derivatives, and again, there'll be a few, you're going to see with the second one, you're going to have a negative exponent as a derivative. But I think you'll be able to handle it. And again, just go ahead and give a few tries. Don't be afraid. You get the 3 tries, and you've got like over 50 chances, so you can always ask for a new problem, which things will change a little bit, but I think you'll see that they're pretty clear. Again, this one, you've got the 2 equations. Solve one of them for x or y. I would probably solve this one for x. X equals 10 minus 2y. Substitute that in over here. Take your derivative. Set it equal to 0. You'll find, in this case, obviously we're looking for minimums, and go from there. Okay, and nothing hurts. And once you've got it into one graph, into just either x or y, you can also graph it. Notice f equals x squared plus y squared. You can't graph that, at least not in the calculators we have. But if you solve this for x or solve it for y, then you've only got one variable, and you could actually graph it, and you'd see where that minimum or maximum is. Okay. Another one, except we've got 3 and we've got 2 equations. So again, more complicated, but solve each of these. It looks like I would probably solve both of these for y. No, what would you do? Solve one for x, so you could substitute x in terms of y. Solve this one for z, so you'd have z in terms of y. Yeah, I guess that's what you're going to, because each of the common thing is a y. So this just gives you a little bit of mathematical playing with things. But again, we're supposed to have applications. And again, I'll be happy to help you with it. And they have a few helps here. Okay, but get this down to just an equation in one variable, and you can do it. It'll be an equation in terms of y's by getting this into, again, when you want the y, but you want to solve this one for x, you want to solve this one for z, and then when you substitute back in, you will have a single equation that only has y's in it. And then you want to take its derivative, and then you want to set that equal to 0, and you'll get a value, and then you plug those back in to find your x's and your y's, your x's and z's, and then you'll get your maximum. Okay, so far so good. We'll see. But kind of the journey seemed like it's kind of, at least you have kind of a roadmap, and then give it a try, and we'll try to give you more time so you have time to work on it here if you'd like. Okay. And then we'll start seeing here, I'll do maybe one of these. These are going to be geometry type problems. And so we're going to be either looking for perimeter or area. Okay. For a rectangle with a perimeter of 20, to have the largest area, what dimensions should it have? Enter the smaller one first. So what does a rectangle look like? Like that. So that's a rectangle. And what we know is that if we go all the way around this rectangle, it's going to be equal to 20. Okay. And so we know with the rectangle, we've got a shorter side and a longer side. So we'll call one of the sides x, and I guess we call the other side y. Okay. And so what we're trying to do is get the largest area, which is another word for maximum area. And what would be the area of this rectangle? X times y. Okay. But what's our constraint, or what's the information that they gave us? Perimeter of 20. And so the perimeter is what? There's an x here and an x here, a y there and a y there. So it's a 2x plus 2y. So this is our constraint. This is what we want to maximize. And again, we're doing exactly the same thing. We want to get either just x's up here or just y's. So we take the perimeter formula and we solve it for either x or y. Okay, so I would maybe subtract 2y from both sides. So that gives us 20 minus 2y equals 2x. Divide both sides by 2. And you're going to see x equals, I guess this 2 can go into 20 and to 2. So it looks like you get 10 minus y, so x is equal to 10 minus y. Plug that in for y, plug that in for x. So your new area formula is going to be 10 minus y times y. Distribute it, take its derivative, set it equal to 0, and you'll get the maximum. You'll get the y value that gives you the maximum. And then once we have the y value, what do we have to do? Plug it in here to figure out what the x is. And once we got the x, take x times y, and that gives us our maximum area. Okay. So this one is really like the ones we've been doing. It's just they gave us the words and we had to set it up. We had to set up the equations. Questions? Want me to go a little further?
Yeah.
Okay. Okay, so for this one, distribute out the y, 10y minus y squared. So this is our area just in terms of y. So we're going to, since we want to maximize it, right, make the largest, we're going to take its derivative. So let's just find some space to write. So the derivative of a is going to be 10 minus 2y. Is that right? This derivative of this is 10. Derivative of negative y squared is negative 2y. We set this derivative equal to 0. So 0 equals 10 minus 2y. Oh, yeah, we'll be okay. Subtract 10 from both sides. So you get negative 10 equals negative 2y. Divide both sides by negative 2. That's going to give us y equals positive 5, which is good. I thought we were going to get a negative number, and that's not good for the length of a rectangle. It's got to be positive. So what do we do with that? Come back to our perimeter function. We're going to plug in 5 for y, and then figure out what x is. So then we get 20 equals 2x. 2 times 5 is 10. Subtract 10 from both sides. So then we get 10 equals 2x. Divide both sides by 2. X equals 5 as well. So what kind of a rectangle do we have? If x is 5 and y is 5, it's called a squared. And you'll find this out that the square of the rectangle family, squares maximizes area. If you want to maximize your area, make a square, not a rectangle. Rectangles are not good, don't make good use of the area. So if you've got limited resources, make squares. Okay, and we're not quite done. We've got x is 5, and we've got y 5. So but they actually want, well, actually they want us. And so now the question, they want the smallest one first. So which one is smaller? 5 is small. They're the same. So hopefully it understands that. We'll put it in and let me save this, and then just come here and say 5 and 5. Yeah, it liked it. Okay, so just so again, that's what these ones are. They're a little bit of a brain teaser, getting you thinking through. You've got to set them up. But after you go, if you start with the early ones, you'll be doing this enough times. You'll take one equation, solve it for x or y, substitute that in for the other one so that you only have one variable. Take the derivative of that function, set it equal to 0, that gives you a maximum for one of the values. Plug that back into the original, so you find that other variable, and then do what you need to do to find the maximum minimum. So it's kind of like, but that's kind of how all of these kind of go through. Okay. And this one, they want to have a smallest rectangle with the smallest perimeter. So again, you'll set it up the same way. Draw a rectangle. Put one side as x, one side as y, and get it set up. Area of 361. So this is one I wanted to show you because this is going to be a little challenging, I think. How many iPods should be manufactured in order to maximize cost? Now this one's not too bad. This one, you take its derivative, you set it equal to 0. That'll tell you where you have minimized cost. Wait, sorry, it's a word that I missed. Average cost. Okay, this is the one. It's a little trickier. You might be tempted to just take the derivative of the cost function and then go forward, but you don't want to do that. What we want to do with this one, and I won't do it all, but I'm going to help you set it up, is we want to minimize the average cost. So if this is the cost, and we're making X iPods, let's say it's 1,000 iPods, how would we find the average cost? If we knew the total cost was, say, $1 million to produce 1,000, how would we find the average cost? We would take the total cost and do what? Divide by how many we made, right? So average is total cost divided by the number made. Well, how many did we make? It doesn't tell us, but it says that we are manufacturing X. So I think we might have skipped over this, or we might have done a few of these. So the average cost function is simply you take the cost function divided by X. So the average cost function is C of X divided by X. So then we get this function here, 36,100 plus 100x plus 0.01 x squared, all divided by x. Okay, that's the function you want to take the derivative of. That's the function you want to minimize, because they want to minimize the average cost. And then once you have the average cost, it'll tell you, once you minimize it, the x value you get will be how many iPods you should make, and then to get the total cost, you plug it back into the original function, right? So this function here is total cost. This function here is average cost. Now you could use the quotient rule here, or if you're like me, you'll distribute this x through so it's 3 different terms, and you'll take it the derivative one step at a time. I think that's probably going to be easier in my book. But the other one might not be too bad either. But so what I would do is I would rewrite this as, so divide each of these by x. So I'm going to get 36,100 x to the minus 1, right? Because it's going to be over x, and I move it up. This one, the x's are going to cancel, so that's plus 100. That's going to be nice when I take the derivative. That becomes 0. And then when I divide x squared by x, I'm going to have just plus 0.01 x. So notice now this is maybe a little easier to work with than doing the quotient rule. But you could do the quotient rule if you wanted to. But it's just like in math, there's an easy way and a hard way, and what's easy for one person might be hard for another, so it's the variety. I would just take the derivative of this as the average cost function. So this is still C of x over x. It's just distributed out and maybe a little easier to take its derivative. Again, you should get the same answer. And then once you get the derivative, what you want to do, so we'll take this derivative, whatever it is, set it equal to 0, and solve for x. You okay with that? Or do you want to see one more step? One more step, okay. So the step, taking the derivative, right? The exponent's -1, that comes down. So we're going to have -36100, and this is going to become to the -2. Should I write it in? Oh, I'll just put it here. That's 0, derivative of 100. The derivative of here is just going to be 0.01. I was hoping you would have said no because I'm not sure what to do next. Okay, so we need to solve this first. So it's all equal to 0. Let's see, how about if we subtract 0.01 from both sides? Does that seem like a reasonable thing to do? And then I'm gonna rewrite this x to the minus 2 as negative 3, 6, 1, 0, 0 over x squared equals minus 0.01. What should I do with that x squared? It's in the bottom. Multiply both sides by x squared, that'll bring it up to the top, and then I can deal with it. I'm not very good at dealing with fractions. We could do it. So that's sort of the key, is we do x squared on both sides. The x squareds cancel here. Again, we're assuming x is not equal to 0. If we end up with x equals to 0, we're going to have some problems because, well, x equal to 0 means we were closed that day. We didn't make anything, so that's not going to do good. So what do we end up with? This is getting messy. I didn't realize I'd need this much room, but we had negative 3, 6, 1, 0, 0 equals negative 0.01 x squared. Any suggestions? Yes. Excellent. So we isolate that x, so we'll divide by negative 0.01 exactly. So then we end up with, I'm going to put it way up here. So we get a positive value, and then when you divide by 0.01, it basically adds a couple zeros onto the end, I think. Someone might want to check me on that. So we get 36, 1, 0, 0, 0, 0 equals x squared. And then take its square root. You get a plus and a minus. The minus is worthless because that's negative, so you're not going to make negative iPods. So then the positive value of this. So we just need its square root. So take the square root of both sides, and that gives us x equals, is that like a 6 something? What do we get? Anybody? That's 3,610,000. How much? 1,900. 1,900. Oh, I got a calculator here too. So let's just take 1,900 and square it. And that, yeah. So we should make 1,900 iPods a day to minimize the average cost. So with all of this in here. But is that, did I lose anybody? Not completely? Okay. So 1,900. How would we, what? Yes, in this function here, we plug it in for x, and that will give us the total cost of producing the 1,900. And again, you could do that either through your table or you could just do it on the screen. See what that's 36,100 plus 100 times 1,900 plus 0.01 times 1,900 squared. I get 262,200. Anyone else? So again, plug in X into this formula here. 262,200 is what I got. So make 1,900 iPods. Let's save all of that. Submit our answer, and hopefully we're right. If we're not, I don't know what to do except cry.
Making a big number for the average cost of an iPod?
Let's see, the 1,900 is, if we make 1,900, we minimize the cost. What is the result? Oh, thank you. Read the question. That's one thing I'm terrible with. Okay, they want the total cost. I didn't read it was the average cost. So yes, take that number, divide it by 1,900. So don't use the original, or I guess use it, but then divide it by the 1,900 to get the average. I probably would have got there, but not as quickly as without your help. So divide it by 1,900, and you're right. You saw that. That's pretty.
Yeah.
So the average cost is $138. Yeah, 262,000 for an average cost, and they're selling them for what, $200? How could they ever make money? So the average cost was 138. Good. And again, just read the questions. I tell myself that every day, but I never listen. Because it's more fun to just move forward, and that's what's nice with these machines. They tell us when we're wrong, and then we come back, but just be careful. It's all in the writing. That's why sometimes I'll read it backwards. Is that okay? Mm-hmm. So again, just, make sure you're giving them the answer they want. Of course, if you're running the plant, your interest is how much does it cost me each day to do all this stuff. So 262,000 is what you're interested in. But if you're in marketing, you want to know what's the average cost, because we better price them, so that we make the money off of it. And then again, you could do all the sorts of other analysis on it. This one's a similar one, but it's not average cost, but it wants, let's see, what is it? This is the cost of controlling emissions at a firm raises rapidly, and the amount of emissions reduced increases. Here's a model. So this is some factory, and if they can reduce the emissions output, it costs them money. Q is a reduction in emissions in pounds of pollutant per day, and C is the daily cost to the firm. So they want to know what level of reduction corresponds to the lowest average cost per pound. So average cost per pound, again, it's going to be just sort of like that last one. To get an average, you've got to divide. So the function you're going to be working with is the cost, C of Q, divided by Q. So that's going to be 5,000 plus 97 Q squared divided by Q. And again, you might want to distribute that just like the last one, take its derivative, but just make sure you're giving the right answers. This one, it wants average cost, and it wants pounds of pollutants per day, and then what would be the average cost. So similar to what we just did, but instead of dealing with iPads and average costs, we're dealing with air pollution and cost per pound of pollutants. So very similar. And again, in business, we oftentimes deal with averages because we want to average cost over. So that's where the division comes in. That's where the quotient rule is important, along with the other stuff. Okay. And I think, let's see, where are we at? This is a question. What number is it? They don't have numbers on them, do they? I can tell we're almost there. There's this with a big word problem, budgets. Here's another big word problem. So these are your applications. 3 problems at the end, 4 problems at the end. I'm going to let you go ahead and take a look at those. What we can do if you run into any major hurdles where you just can't get through it, and that doesn't mean you work for 2 minutes and could get through it, but if you work for about 10 minutes on this and get stuck or something, again, we've got about an hour if you want to hang out and work on it here, or you can email me a question, and I can either help you out a little bit with, you let me know where you're at, or I can also make a little video of these. So there's these 4 that are going to be get through the problem solving type things. What I'll do over the weekend is I will come up with a practice test for chapters 11 and these little 2 for chapter 12. So there'll be a few max and mins. The other question, the test was supposed to be 15 questions, but I guess I forgot how to count. I only did 14 of them. So what I'm going to do is it'll be out of 150 points, and I'll add 10 points to everybody. So everyone's sort of like, you get 1 question right for having your name on the test. And if you logged in, that put your name on the test. So just to make things even out.
Wait for the last test we just did?
Yeah. It's actually, there's only 14 questions, and it was 10 per question, so it's 140 points. And the way I had it planned out, it was supposed to be 150 points. So the easiest way for me to do it is just add 10 points to everybody's score, and then my system works out a little bit better. So it equalizes it pretty good. Again, get the test corrections into me either online. You can email them to me. So scan in a document or something. But just again, what I'm looking for some explanation that shows you understand how to get the question correct and that you've got the correct answer. If you've got the correct answer, you'll get half the points back at a minimum. Good explanations could get you a few more. Over the weekend, I'll come up with a next test for chapters 11 and 12. There'll be a practice test, and if I can get it done, I'll have the actual test. It'll be 15 questions as well. Well, this time it'll really be 15, hopefully. But it'll be another 15-point question that is much like the practice test. So again, it's really what I do with my test is just, if you've worked through the practice test, you should be able to come into the test and it should be very similar. And if you're missing something, it's because the problem is a little different or something, but you should be able to do well on all of them. And my goal is to have that done by the end of the weekend so that next week you could start into it. I'll leave it open until the end of, well, what should I do? If you really need it, I can always push it, but let's maybe give it, again, another week and a half or something. I don't want to squash you too much, but I also don't want to give you too much, think about too much time, and then you get too far behind. But as long as we get it all done by the end, we're okay. But if you can get it done within about a week and a half, that would be good. And then we would just have the one last test, which is just really going to be mostly over 13 is only 3 sections, and then there's some applications from 14, so just 4 sections as the last test. And then again, if you've done good on all 3 of those, fairly good averages, and you did some of the extra credit, you probably have an A without even taking the final. Okay, and that's sort of the goal I'd like everyone to try to shoot for. Makes it a lot easier for me, but I'll have a final prepared one way or the other for those who need it. Okay, and again, just a reminder: if you want to retake the last test, get the corrections into me so I can review those. I'll update your grade, and then I'll also make a retake test for that, and we can make that available if you want to do that. Okay, any questions, concerns? All right, you guys are great. Thanks.